Hey, what's up, guys? This is Sheng here. So today, let's take a look at LeetCode number 721, accounts merge. So you're given like accounts, right? A list of accounts, and each element of accounts, right? So it's a list of a string. So where the first element of each item of account is a name, and the rest is the emails that representing that belong to this account. And our task is to merge those accounts by the emails. So which means that if two accounts have any common emails, we need to merge those two accounts together. And note that even if two accounts have the same name, they may not belong to the different they may belong to the different person, as the people could have the same name. So which means that when we do the merge, we should only use the email, not the name, because the name could be duplicated, right? And but all their accounts, right, definitely have the same name. So which means that if we have, like, for example, we have some like examples. So we have like 3 Johns, right? We have John 1, John 2, and John 3. And John 1 and John 3 have the common email, which is the johnsmith@mail.com, which means that we should merge those two John together. Okay. And then in the end, when we output the data, right, we need to output a list of lists, where the first one is the name of the account, and second one is and the rest is the sorted, right, emails. Cool. So to solve this problem, obviously this is kind of like the emerging problem. Basically we have two options we can do here. So the first one is a DFS, and the second one is a union find. So for the DFS, basically we need to build like the graph, right? So the edges for the graph is so basically the vertex for the graph is each email, and the graph and the edge of the graph is basically if two emails belong to the same group, then we'll draw an edge between those two emails. So which means that when we build a graph, right? For example, we have like this first drawing here. For all the emails for the same account, we're gonna build a graph. We're gonna build the edge. Basically, we're trying to connect all those emails together. And yeah, and once we have the graph created, we can just simply we can start with any of the emails, and then with a certain email which we haven't visited before, we'll do a DFS traverse, and then we'll use the graph, try to find all the neighbors that we can reach. And so after each of the DFS, basically all the neighbors that we can reach from the current DFS search will be the emails belong to the same group. And now we have the emails. The only thing left is that we just need to get the name, right? And for that, we're gonna maintain like another email to name hash table to help us find the name given the emails. Cool. So let's try to implement the DFS approach first. So we have a graph, and we have a default.dictionary.set. Okay. So the reason I use set is that I want to avoid duplicate edge, right? And then I need an email to name equals to this one. So for account, in accounts, right? Name equals to account dot 0, right? And then to build, now we need to build the edge for all emails. Okay. So we have email 1 and then account 1. Basically, I'm building the edge for all the emails, all the remaining emails to this email 1, which is the first one. You can choose any of the email, but I'm just using the first one. And then we have like email to name dot email 1, right, equals to name. And then for email 2, basically for all the remaining emails, right, I'm building an edge from email 2 to email 1. Oh, one more thing, this edge should be a bidirectional because there's no sequence. So here actually, remember we have some accounts who only has one email. And in that case, right, since later on, what we will be doing is that, when we have like answer and then we have a scene, right, set. So here, when we start building our answers, we're gonna loop through all the emails in this graph. That's gonna be our first for loop here. So which means that we need to have like emails appear, each email appear in this graph. So if we start looping through from the second one here, if we have only has one, actually, you know what? We can start. We can still start from this one because when we do the loop here, we can simply loop through. We can use this one, email to name, to loop through to do the final loop here. So yeah, I think this is fine. Because I was thinking that if we try to use a graph here, we might need to start from one to build like a edge for the email one itself. But we already have like the email to name dictionary who has all the emails. So which means that we can simply just do this. And we create two edge, right? From email 1 to email 2, and then from email 2 to email 1. Okay, and then of course also need to maintain this email 2 to name. Yeah, here if the same email gets updated twice, I think it's fine because the set that's why we use set, and that's why here the dictionary is fine. We can just update it multiple times. Okay, cool. So with that graph created, and now we have this email, right? From this loop through each of the email. So if this email has not been seen before, which means that if this email has not been traversed from previously group, then we can start our traversing, right? So the way I do it, I use the stack to the traverse, and then we have a scene dot add, right, to the email, and then we need the emails list to store the current emails, the emails for the current group, and then while stack here it's just like the DFS template. We have current equals to stack dot pop, and then emails dot append of the current, right? So for neighbor in the graph dot current, okay, and if neighbor not in scene, then we should do a stack dot append neighbor, and then the scene dot add. So this is just like the DFS template, okay. And after this while loop here, right, we have everything. We have all the emails that belong to the current group, right? So which means we can just populate the final answers, which will be the first one is a name, right? It's going to be the email to name. We have email, and then the second one is basically a sorted version of the email list, okay. And then in the end, simply return the answer. Yep, I think that's it. Run the code. One. Oh, I typed too fast. Okay, accept it. Yeah, so this one passed, right? So, and for the time complexity, I mean, to build this part, I think that's the gonna be the, let's say we have, so basically this part is pretty straightforward. Basically, it's everything that's inside accounts, right? And so for the second part, since we have the sorted list here, so I think the main time complexity, the dominated time complexity will be the sorting part. So let's say we have m equals to the length of each account. So 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 basically the sorting will be like what? Will be the sum of the m times log m, right? We loop through everything from from equals 0 to n, right? Where n is the total number of accounts and m is the length of each account. That's going to be the time complexity for this one. Yeah. Yeah, cool. So that's the first DFS approach, right? Pretty straightforward, huh? Right. So let's try to implement that the union find solution. Okay. So for the union find, first thing first for the union find, we need to have like a parents uh, collection that to store the current parents or for the parents for the current element. So for this problem, since the email doesn't have an index, if the node has an index, then we can use like a list, right? So then we can just use the index to find the parents. But for this one, the email doesn't seem to have like index. That's why to find the parent for certain emails, I'm just going to use like a dictionary or a hash table to do that. And similarly, we also need to maintain this one, right? Cool. So okay, so let's try to populate these parents, because at the beginning for the union find, we need to initialize the parents for each of the node to be itself. So in account, so we have a name, right? Similarly, we have account 0, and then for email in account starting from 1, right? So first, an email to name it's going to be email equals to name. Second, its parents of the email will be itself, right? So now we have initialized these two things. And yeah, so now we can start implementing the two method for the union and find. So the first one is the find. And so basically if the parents of x is not equal to x, right? So do a parents dot x equals to find parents x. And then in the end, we return the parents. So this is just like a template of implementing the find method with the path compression. So if you're still not familiar with the union find implementations, you can find a lot of explanations regarding those two methods, right? So that's a find, and then we have a union, x and y, right? So we have root 1 find x, root 2 equals to find y. So if r1 does not equal to r2, then we assign parents.r2 to r1. So here I'm not using a union by rank. So ideally, we should have like another rank list to maintain the rank for each of the group. And when we do the union here, we only union the group. We always union the group with a lower rank to the group with higher rank. But here to make it simple, I'm just always union group 2 to group 1. Cool. So now we can try to union those emails, right? So for account in account, right? And then we have similarly as how we build the edge in the DFS, we will try to union the all the emails with the first email. So we have email 1, and then we have account 1, right? And then we're gonna union all the emails, right, to the email 1, to email 1, which is going to be the email 1, then email 2. Okay, so after this union here, we have the groups we need. The only thing left is just to output the groups. So first, I'm going to populate the group we have here. Okay, so for each email, right, in parents, we can use the root, the find method to help us find the groups, the group root for the emails, and then we're gonna use that root as a key to populate these groups, and we append this email. Right, so after this one here, so we have the groups. So basically this group is everything we need, because the key for this group will be some emails, right, as the root for this group, and the value will be all the emails belong to the same group, which is exactly what we need here. And the last step is just to sort the emails and then to get the name. So we have a key in groups, right? And then the answer will be this one. Basically, the first one is the name, email to name dictionary. We have a key, and then similarly, we have sorted of the groups of the key. Okay, and then return answer. Okay. Okay, cool. Submit. Yeah, so this one also works. Yeah, I guess that's pretty much it is, right? The for this one, we don't have to worry about union email 1 with email 1, because email 1 is already like the a node, right? So we don't need to worry about that, like how we handle the edges, right? In this in the DFS search. And here we're only union those two different nodes together. Cool. So yeah, I mean that's the union find, and the time complexity for union find is similarly as a DFS, because it's also bounded with this kind of sorting here. Yeah, because for the union find, even though we have this kind of two method that we need to remember, how can we implement that? But if, as long as you can remember those templates, the remaining should be pretty straightforward. Even I think for me personally, I feel like the union find is a little bit it's more straightforward than DFS, because after the unions, you have everything you need in this parents dictionary, and the only thing left for you is just to how can you group those things together, and it's pretty straightforward. Basically, as long as we have the root, right, for each of the group, because for each group they will have the same root, and we can simply use the same root as a key to group those kind of elements together, and then we just do the output in the end. Cool. I think that's everything I want to talk about for this problem, and thank you for watching the video, guys. Stay tuned. See you guys soon. Bye-bye.